Hello everyone and welcome to this session. I am Rebecca McVicker and I am the Product Director at Gamlen. Today I'm going to be talking to you about understanding compaction using USP 1062 data. First of all, why do we want to analyze compaction? This is of course to make better tablets, and a good tablet has to meet a lot of criteria. They have to be strong, porous and free of defects. The difficulty here is that these properties are often fighting against each other. A tablet that's very porous is not going to be very strong, but a tablet that is not porous enough is likely to show capping and lamination defects. To avoid defects like sticking and picking, you need your blend to be well lubricated, but a blend that is overly lubricated, the particles within the tablet will not adhere to each other and you end up again with a weak tablet. So you're always trying to balance these factors against each other, and this is what makes tablet formulation and manufacture particularly challenging. Ideally, we would want to know if our formulation is meeting all of these criteria before entering full-scale manufacture, and this is where compaction analysis comes into play. The United States Pharmacopoeia published chapter 1062 a few years ago on tablet compression characterization, and the quote there has been taken from that chapter, and it essentially says that although we've been making tablets for over 100 years, we are still seeing the same problems we always have. We're still seeing capping and lamination, sticking and picking, and the problems associated with low tablet hardness. In fact, in our office, we have a book from 1906 that outlines the same issues. And this chapter, it gives the USP recommendations on the data we should be generating in order to avoid these problems happening. The data that they recommend generating can be summarized by the compaction triangle. And here we have three different measurements. And by making these three measurements, we now have three different relationships, and the tabletability, the compressibility, the compactability. And each of these relationships gives us a way to evaluate or compare different tableting materials. And in order to generate this data, you need to create a series of tablets using different compression pressures. You need to be able to accurately measure the compression pressure. You then measure the dimensions and the weight of the tablets that you've made in order to calculate solid fraction. And then finally, you break the tablets in order to measure their tensile strength. You can see off to the side of the triangle this bit here saying that we measure the breaking force and the compression force, but we always convert to compression pressure and tensile strength, and this is in order to account for the tablet dimensions. By doing this, we don't have to be working with the same size and shape tablets in our analysis that are being used in production. And that's very important because that takes it from being a technique that is specific to one type of tablet to making it an actual material characterization technique, and you're now looking at the fundamental compaction behavior of a material itself. The one piece of information you need to have about your material before you would start this type of analysis is that in order to calculate solid fraction, you need to have the true density of a material. This, for most well-studied excipients and APIs, will be something that can be looked up quite easily. It can be measured by helium pygnometry, and if you're working with a blend, it's an additive value. So if you simply know you can calculate the solid fraction of a mixture so long as you have the true density of each component. If you simply do not have the true density value available, you still have the tabletability relationship to work with, and this is often the most sensitive piece of information to differentiate between samples, and it's often the most useful piece of information. I should say, if you're not familiar with the term solid fraction, it can be easier to think of it as the inverse of porosity. A tablet that has a very high solid fraction is going to have a low porosity. So a tablet with a solid fraction of 1 has 0 pores, or 0.9 would have 10% porosity. That is why you analyze compaction. So next is, how do you go about analyzing compaction? It's carried out in 3 steps. First, you make the tablets, then you measure the tablets, and finally you break the tablets. You want to make the tablets in such a way that you can accurately measure the load that's being applied to the tablets during compaction. Then measuring the tablets involves weighing the tablets and measuring their dimensions, the thickness and diameter. And finally, you break the tablets, and if you're familiar with a hardness tester, then you'll be already familiar with this. And from these measurements, you understand your powders. For a typical analysis, I normally recommend that you would use 5 different forces to make 3 tablets at each force. This gives you a full profile as opposed to a single point measurement. A typical analysis using our equipment would take less than 2 grams of material and takes about half an hour for a complete test. Next, I'm going to talk a bit more about the 3 relationships in the compaction triangle and talk about what they can tell you about your formulation or material. The first is the tabletability relationship, and this is how the tensile fracture stress of the tablets change with compaction pressure, so the strength of the tablet. I would say that the tabletability relationship is the most useful relationship described by the compaction triangle. It's useful both when you're building up a formulation, but also when you want to look at alternative suppliers or alternative sources for a material. So in that case, you could look at an excipient or even an API by itself and look at how strong a tablet that material makes. And here, not only are the absolute values useful, but the shapes of the profiles also tell us a lot about what's going on. We tend to presume that when you increase compaction pressure that there is a resultant increase in the strength of the tablet. But for a lot of materials, this is only true up to a point. A lot of materials, the increasing hardness or strength of the tablet will plateau at a certain point as compaction pressure is increased, or it can actually decrease, which is when overcompaction starts to happen. And I have a slide on that further on, but that's a very important observation from the tabletability data. In the graph here, we can see the tabletability results for 3 formulations. For each one, 15 tablets were made and analyzed, so that's what is giving us the full profile. We started with formulation A, and then changes were made to that formulation, resulting in formulations B and C. You can see that the change from formulation to formulation B has resulted in minimal change to the tabletability behavior of the formulation, whereas the change that gives us formulation C has really significantly impacted the hardness of the tablets, that we're now getting weak tablets that we would suspect that it's quite likely that we're going to see production problems related to low tablet hardness for these tablets. It's also interesting to see that for formulation A and B, and C in this case, that the shape of the profiles for each of them shows us that as we increase the compaction pressure, that there is a resultant increase in the tablet strength. So that will be another sign of good tabletability behavior here. The next relationship is compressibility, and that describes how the solid fraction or porosity of the tablets changes with compaction pressure. This is important because a tablet that has a very high solid fraction will be likely to cap in production. A very high solid fraction is also a problem because without a certain level of porosity, liquid can't penetrate into the tablet, and this will slow down your dissolution times. While low solid fraction and high porosity will result in weak tablets. Companies often have a upper solid fraction limit that they don't want to work above. They don't want formulations that are above a certain solid fraction limit with a very low porosity. 0.9 or a solid fraction of 0.9 would be typical, as shown in the graph. Compressibility is a relationship that's very useful when you're building up a formulation to make sure that your final formulation and your final product, that the tablets will have a reasonable level of porosity while maximizing tablet strength. But it's not as useful when you are simply comparing different samples of the same material. Say you're looking at different sources of MCC, for example. That material simply from different sources, you won't see a difference in the solid fraction data. If it has the same composition, you will see the same solid fraction results. The exception to this would be if your different sources of your material actually have different solid state forms. In that case, you will see a difference in the solid fraction data. In the example here, you can see that our formulation A and B are showing very similar compressibility behavior, whereas formulation C, there's a significant difference. And from this, I would say that the difference between A and C, that was a compositional change, whereas the change from A to B is likely to be more a change with the process, that the change that happened there did not impact the composition of the formulation. The final relationship is compactability, and this is how the tablet tensile fracture stress changes with the solid fraction of the tablet. And this is another relationship that's particularly useful when you're carrying out formulation. Here, if you're getting data similar to what you see in the example, where formulation A and B are looking quite similar to each other, but formulation C, here we have tablets that has the same solid fraction as some of the ones in formulations A and B, but these tablets have been measured to have lower tensile fracture stress values, so these are weaker tablets. The fact that the tablets have the same solid fraction, but that the formulation C tablets are weaker, this means that the difference in strength between these tablets is not due to a difference in the level of pores in the tablet, but due to something more fundamental about the materials in the tablet itself. You may have noticed in the recommendations from chapter 1062 that there's nothing in the compaction triangle that covers lubrication or evaluating lubrication. And this is of course essential if you want to avoid sticking and picking issues. The way we approach this, the way we evaluate lubrication, is by measuring the detachment and ejection forces. And essentially these forces are the forces required to get the tablet out of the die after it's been compacted. Once the tablet's been compacted, the tablet will be stuck to the base of the die. So the detachment force is the force that is required to detach the base of the tablet from the base of the die. Next, the tablet is pushed out of the die, and this is the ejection operation. And the force that requires is the ejection force. It's pretty intuitive to think that if these forces are high, then you're going to have sticking and picking issues, that you have a poorly lubricated blend. And these operations are equivalent to what happens on a full-scale tablet press. The only difference is that on a full-scale press, the ejection of the tablet happens before the tablet is detached. And sometimes you might know the detachment force as takeoff force. Next, I'm going to take you through some examples so you can get an idea of how compaction data can be used. The first example is a lubricant comparison. And here we're looking at 3 different excipients, lactose, Lubripress and mannitol, and looking at whether magnesium stearate or sodium stearyl fumarate is the better lubricant for each one. On the slide are the tabletability graphs on the top. So this is how the strength of the tablet changes with compaction pressure. And on the bottom we have the ejection stress graphs. So these tell us how effective a lubricant each lubricant is in each case. I'm only showing each of those graphs in this case because they're the most relevant to this study. When looking at different lubricants, you want to know how effective the lubricant is, but also its impact on the strength of the tablet. And also because you don't need to have the true density of the material to generate any of this data. The tabletability and the ejection stress profiles don't depend on the true density of the material. So if you don't have that, you can still get this data. In the first example, which is lactose lubricated with magnesium stearate and sodium stearyl fumarate, here we have the magnesium stearate tablets are the solid circles. And it's pretty obvious from this top graph that the magnesium stearate tablets are stronger than the SSF tablets across all of our compaction pressures. And when you look at the lower graph, there isn't a significant difference between the two sets, but you could argue that the magnesium stearate tablets are showing slightly lower ejection stresses, so it's a very slightly better lubricant. So given this data, if you were choosing between these 2 lubricants for lactose, then magnesium stearate would be your better choice as the tablets are stronger and slightly better lubricated. Then the same study for Lubripress. Lubripress is a premix of several different excipients. Here, the SSF tablets are the stronger tablets, but only up to a point. After 300 megapascals, you get this drop off in the strength of the tablets. And this is an example of overcompaction happening, where we're hitting the tablets too hard and they're actually becoming weaker. In the lower graph, you can see that again the magnesium stearate is also the slightly better lubricant. We have lower ejection stress values compared to the SSF. If everything was equal, then I would say to choose the magnesium stearate as the lubricant in this case because it's the better lubricant, but it's also the less risky choice. The tablets aren't as strong below 300 megapascals, but you don't have the risk of this overcompaction happening. So it's the less risky option. If you knew for certain that you weren't going to be increasing the compaction pressure above, say, 200 megapascals, and you really needed that extra bit of strength in your formulation, then you might consider the SSF, but it wouldn't be the ideal situation. And in the final example for mannitol, there is no significant difference between the strength of the magnesium stearate and SSF tablets or the ejection stress values. So it's both of the lubricants are equally as effective in this example. So here you could just choose your lubricant based on any other factor, whether it's the one that's more readily available or the one that's cheaper or so on. If you were doing this full study in real life, you would probably do different percentages of the lubricants, and you could also look at blend time. But this example is just to show you how easy it is to see the impact of your choice or a change on the compaction behavior of your formulation. The second example is an alternative supplier evaluation. So say you're using one source of MCC, but you're looking maybe to de-risk that supply or looking just for alternative options. Here again, we have the tabletability and ejection stress graph to keep things simple to not show the full data set. Here, let's say you were working with MCC source C and you were considering sources A and B. From the tabletability graph, you can see that if you change to source A, you're looking at taking a hit to tablet hardness. So the tablets from MCC source A are weaker than source C, but source B is showing very similar tablet strength to your current source. Then looking at the injection stress graph, you can see that if you change from source C to source A, you're actually getting an improvement in how well lubricated your blend is, that this drop in the injection stress values, meaning that source A would have a lower lubrication requirement, whereas changing to source B has a higher lubrication requirement. So from this data, you would know the impact of your change on your formulation. You would know if you change to source A, you might get weaker tablets, but you might get tablets that are less likely to stick and pick. But changing to source B, you get stronger tablets, but ones that might be more likely to stick and pick. So you could make that decision. You'd probably take into account the history of your formulation and whether it has had a tendency to do any of these things in the past. But again, it's just to show you how easy it is to make these informed decisions using compaction data. Finally, a bit more about the risk of overcompaction. And as I said, we tend to think that when we increase the compaction pressure applied to a tablet, that we will end up with a stronger tablet. But this isn't necessarily true. There's actually 3 different types of compaction behavior you see when you increase compaction pressure. These are described in the graph. Type 1 is the one that we hope for, that with the increase in compaction pressure, we get a corresponding increase in tablet strength, although the increase becomes less and less as the compaction pressure increases. And this is the behavior we would associate with MCC, something that has, excellent tableting properties. The more common behavior would be type 3, where you have an increase in tablet strength up to a point with increasing pressure, but after that, the strength of the tablet plateaus, so there is no increase after that point. So at that point, any further increase in compaction pressure, you're just wasting energy essentially by hitting the tablet harder. Type 2 is the risky behavior, and this is what we don't want to see. You have an increase in the strength of the tablet with increasing compaction pressure, but at a point this tips over an edge and you now have tablets that are weaker than at lower compaction pressures. This is overcompaction, when you're now hitting the tablet so hard that you're creating flaws in the tablet. And this can be a real problem in production, because if you have a material like this and you don't know it, then when you might see that tablet hardness might be trending down a bit, the instinct is to increase the pressure on the tablets, and you could actually make the situation a lot worse by tipping it over this edge and actually making weaker tablets than you had to begin with. So I think that this is something that is very valuable to know when you're going into production. That is everything from me. Thank you for listening, and I look forward to answering your questions.